first thing, the easiest question, PVM and RISC-V are compatible. Not from PVM to RISC-V necessarily, but RISC-V can be recompiled into PVM very, very easily. We expect that we will be a target of LLVM in the next 12 months. Like, the alterations to LLVM are pretty minimal to make it work really nicely with RISC-V, with PVM. But even before then, it's just a very quick translation pass on RISC-V code. I mean, it has to be the particular variant of RISC-V, right? So at the moment, I think it's 32 EC, and eventually it has to be 64 EC for the next thing. But it's easy. So there's no worries on using mainstream mainline toolkits to create PVM code. Good. What services do I expect to see? So I mean, JAM is created for two main things. One of them is to be backwards compatible with Polkadot Relay Chain, and the second is for core play, which is a fairly ambitious smart contract-esque, actor-esque, highly scalable, synchronously composable system, like platform, right? Which would support multiple multiple program languages, so EVM, PVM, and potentially others as well. It would be like, there are smart contracts and there are kind of things that are more like actors, and it could also support just indefinitely running programs. The idea is that it's a very much it's what Ethereum is meant to be. It's a big virtual global supercomputer that can host people's code and run it in a sort of shared sandbox environment. So those are the two services that are really, that's the success criteria for JAM. It must be able to host these two services. What other services might be interesting? I think there are a few things that are currently built as parachains that would make sense as services. The two that I can think of, maybe three. One of them would be like the bridge hub, basically. I think bridges, because they don't necessarily need, because they rely on other consensus systems forming a kind of subconsensus, and the only thing that really needs to be done in sort of Polkadot is checking that subconsensus is correct. You don't really need this collator network, and if you don't need that's the sort of sensible, that's the way that you can figure out, look, is the collator network the optimal solution? If it's not the optimal solution, then probably it's better off as a service or something that sits on a service. So yeah, bridges, so essentially like clients, probably make sensible services. A storage network may also be a very sensible thing to build as a service, mostly because it's like the blockchain element of it is probably not so relevant. What's more relevant is the data I/O element, and you probably do that more efficiently if it's built directly as a service. And the other thing that springs to mind is something that we've mentioned in the JAM chat room, which is building full nodes and running them inside of JAM cores. So like, this would mean we would be effectively bringing other networks under the JAM security apparatus, which means not only do they get extra security guarantees, because they're not being just checked by their own validators, but by JAM's validators as well, but they also get, because they're under a common security apparatus, high-speed messaging between them, which is, at the moment on Ethereum L2s, it's a bit of a big deal. It's very hard for these L2s to communicate securely and speedily between each other. So there are some interesting potential use cases there for JAM. And one like mad thing is just like run Ethereum L1 as a JAM in a JAM core. Just don't forget trying to actually client bridge to it. Just run a full node, right? And this kind of like mad stuff that we can actually start thinking about doing with the level of like performance and bandwidth that Jam brings. I don't have much more than that. I haven't like given it too much thought. I think when we start having real Jam testnets and better tooling and like a service SDK, and we just start coding stuff up, we can actually get a much better feel for what's possible. But at the moment, it's really hard to imagine what might be possible on a system that we can only imagine anyway. It's like imagination squared. My relationship as grey paper author with the rest of the team. So I'm focused mostly on, in terms of my like coding, I'm focused mostly on the on-chain stuff. I've not really touched anything off-chain. So whenever something in the grey paper changes that relates to the on-chain part, I'm usually the one that actually codes it in Rust. This is actually a very good thing because I kind of, I have a very hands-on feel for what's actually going to be possible, efficient, performant to implement. And I'm not just head in the clouds, ivory tower, just writing random math stuff and expecting to pass the problem on to someone else, which I think is to some degree a bit of an issue in certain other communities. That said, I am still very much in touch with everyone there, and the team at the moment in Parity, I think it's depending on exactly who you count, it's about 6-7 people that are working on the Parity implementation of Jam, and this includes like 1 or 2 people on the PVM and a cryptographer. So it's like, actually it's only about 4 or 5 people, and this has to include like the person that's writing the test vector stuff, which isn't specific to what we're doing. I guess that's like most of the questions addressed thus far. In terms of like what to expect and when, I've written a small presentation because I figured this would probably be something that came up. So, you're probably all familiar fairly well with the 01, 02, and 03 versions of the grey paper. And these brought in these laid the ground for all of the all the basic functionality. 04 was a big change with ordered accumulation. This had been, if you actually go all the way back to the Core Jam RFC from like last year in the Fellowship RFC's repo that the Jam is sort of kind of based off. You'll see it being mentioned as a kind of aside. This is something that we might very well want to do, but it's kind of complicated. So, but it turns out that actually, in fact, if we go to kind of open this up, if we go to the issue that I wrote, it's actually necessary to have ordered accumulation for doing basically doing zero latency segment I/O. So you should be familiar by now with the idea that work packages in the refined stage can read and write to this segment, to this DA, to this giant data lake, right? It's like a petabyte, right? Several petabytes big. It's like huge distributed availability system, and they can read and write from it. But it's only mostly coherent, which means what they write into it in one block, they can't necessarily read from the next block, right? And they certainly can't do it like in the same block. If we implement, and then this is something that has to be carefully designed, but if we implement it well, then we can probably end up with a sort of affinity system where if you are on the same core index, if your work package is on the same core index from block to block, then you can read from the block that you last read, from the work package that you last wrote to the block before. Yeah. So you can basically have one work package that executes at like block T and another one that executes at block T plus 1, and the block T plus 1 can read from a segment that block T is written, right? So it's like within the same core, it's totally coherent, totally synchronous, which is a very helpful thing to be able to do. Yeah, to not have to wait an extra block or 2 or 3 before you see what the last thing that you did, what effect it had. Now there's a big issue with this, which is that you may not know the segment root, because the segment root is only calculated once you've actually run through the work package and gotten the work report. And if you're literally just spitting out work packages and all you care about is that, well, I know it was index 4 of the segment index 4 of this previous work package exported, but I never actually bothered computing it, so I don't know what the segment root is. You can't provide this cryptographic reference. And that's what ordered accumulation basically allows. It's not that you get a cryptographic reference, but you get a semantic reference. You can say work package blah, like the hash of the work package, segment index 4, and it will look up that work package hash into a segment root, and it will do so securely. You can do it not insecurely without this, but to do it securely, you really need ordered accumulation. And that's what this says. So that's why we have ordered accumulation. It's not just some whim of wanting to be able to provide some sort of dependency graph. There's actually a very particular reason, which is that we can claim that JAM is that JAM's DA system it gives sensible usage characteristics. Yeah, not that you have to skip 2 blocks in order to read something that you wrote out last time. Yeah, that would be not such sensible usage characteristics. So that took us to 0.4. 0.5, there's already a pull request open for 0.5. It's mostly complete. I'll probably, as long as there are no glaring issues with it, I'll probably merge it in the next day or 2. There are a couple of things that it brings about pre-images after accumulation. So at the moment you integrate pre-images before you accumulate. You're going to switch that around, so basically you can run your accumulation before like necessarily knowing what pre-images are going to be introduced into the block. Generally you want to start accumulation as soon as possible, and you don't want to be, whereas pre-images might arrive on the network over the period that you are accumulating, or over the period that you are deciding what should accumulate. We also have a structured extrinsic commitment. At the moment, extrinsic commitments are just a hash of the whole thing, of this like serialized extrinsic block, right? So you take the extrinsics, all 5 of them, you serialize them into some big, like, I don't know, 15 megabyte block. You hash that, and that's what you put in the header. This is fine, except if you want to, say, distribute parts of this extrinsic individually, then there's no way of proving that this is actually a correct part of this block. Yeah, because you have to either provide all 15 megs of the extrinsic or none of it. You can't like prove that it's the right 90k in the middle. That's why we bring in this structure. It's basically a Merkle tree, but it's not a strict like binary Merkle tree. It's like it's a Merkle tree because we don't need a full binary Merkle tree. It's going to be like lots of hashing and quite complicated to do. So we just instead hash the. We have a Merkle tree of the guaranteed of the reports, because these are the things that you might want to distribute individually around the network, like kind of gossips, not quite gossip, but kind of gossip. The rest of it you're probably going to want to just send directly. You're not going to want to necessarily just distribute bits at a time. Also, the work reports make up the vast majority of the block of this, in terms of like bandwidth, disk space. The work reports make up almost all of it. So it's helpful essentially just to be able to have these things kind of have a separate logistical path to get to the other nodes on the network. There's also some minor change to the availability spec. The number of export segments is included in there, as well as the hash of the segment tree. There's also been a bunch of changes to the PVM in 0.5. The biggest one is that there's 64-bit registers, which should speed things up quite a lot for many common use cases. There's also made clear a very sort of formalized the paging of the PVM. So PVM formally now has 4K pages, and each page, not each byte, can be either inaccessible, accessible just for reading, or read-write. Prior to this, it was each byte, which obviously is kind of nonsensical for a real hardware. There's two new host calls for the inner PVM manipulation, which are essentially allocate and deallocate, and they change these pages from the first host call, which is 0, changes the page from being not accessible to read-write, but full of zeros. And then void changes it from being read-write or read to inaccessible. And by determining how many pages that are accessible there are, this will alter eventually the gas calculations. Gas will become more costly. There'll basically be a multiplier, a gas multiplier, that makes all of the gas be cost more gas. All of the operations cost more gas if more memory is accessible. Yeah? So it's in your interest, there's a program running on the PVM to keep the amount of memory that you can access as low as possible. Why? Modern architectures are fast, but can be very slow if they're hitting memory that is not in the cache. Right? This can have a 100x slowdown. There isn't really an efficient way of deciding whether memory is going to be in the cache or not ahead of time, and if you do it at the time, you're basically talking about trying to catalog every memory access and model a CPU's cache in real time, which is obviously really, really slow as well. But a slight trick that we've come up with is to say, well, look, if there's only 1 megabyte of memory that is accessible, then it's all going to fit in our chosen hardware's L2 cache, which means there is a limit of how fast of how slow it could possibly be to read something. And that's what's going on here. So we want to incentivize programs not to have so much memory allocated, and that's why we have these very explicit allocation deallocation. We're going to introduce another RISC-V extension to the PVM instruction set, this basically bit operations extension. That's not made, we'll see if this happens in 0.5. I know it's being worked on, like prototyped in the Poker by one of Jan's guys in the Poker VM team. If it happens, it happens. If not, it'll be at 0.6. And there are 2 more instructions that we'll add as well, basically mem set and mem copy, and these will be optimized on the host side for doing mem copy operations, with the expectation being that this can be this can have a significant performance increase. Right, so that's 0.5, and as I say, hopefully that's something that will be launched this week. Next week. I expect 5 more minor versions before we hit 1.0. The 0.6 is essentially feature completeness. So all of the stuff that I think should be in the protocol is probably going to be is going to be detailed in the great paper by 0.6. It won't necessarily be the final version of it. It may need some tweaking, optimization, but so Grandpa, there's going to be an actual reference into the Grandpa paper, so it's like unambiguous. I'll fold in the JAM network protocol into 0.6. There will probably be additions as we go on, but this will be specific network optimizations as we understand better the dynamic the dynamics of nodes and trying to push through blocks and author blocks and so on. And we're only going to refine that when we run it on the toaster and actually have larger scale networks running through real-ish applications. There's also this idea of of bringing in one of the additions that has been proposed for the relay chain, MMB, Merkle Mountain Belt, Merkle Mountain Belt, which is basically it's a fairly small optimization on the structure of doing MMRs. It's super. It's like a more efficient Merkle Mountain ranges, but it's still a Merkle Mountain range. It's just you have a slightly different data layout for it. So when you add stuff, there's like an order one computation cost, and your tree depth for stuff that you're most likely to want to prove, which is basically more recent things, is smaller than it would be if you use a regular Merkle Mountain range. But as I say, it's a very minor tweak. So that'll probably go into 0.6. Basically 0.7 will be toaster tweaks. So when we get actual real performance data, empirical performance data for like emergent network behavior by running nodes, hopefully more than just the Polkadot Jam node. 0.8 will be the last main set of tweaks, the last main set of non-security related tweaks, and that will be for when we start prototyping services, start running services on it and say, oh, actually, it turns out that to run this, the core chain service, it's really shitty unless we have this particular PVM instruction or this particular facility, or we need to optimize this particular network operation. I don't know, but like that's where these final application level sort of tweaks will come in. 0.9 is mostly focused around security. It's at 0.9 we should be launching on Kusama and having the protocol be audited, and then 1 is the final thing. Yeah. So 0.6 is focus for getting this feature freeze. There's also a bunch of improvements I want to make to the grey paper, which is going to make it really difficult to read for everyone that is used to reading it as it is, but I think it's actually really important for getting it, because my biggest annoyance with the grey paper as it stands is that I've used subscripts. So when I use subscripts, I sometimes use it for like indexing an element in a sequence, or for naming a field. And although like they're not it's generally unambiguous as to whether it's a field that needs to be done or a subscript, it's still like the same visual language, and so you kind of have to think, hold on, this thing that's being subscripted, is it a sequence or is it a tuple or whatever? And that's not so good. So I'm going to change it so that field names are always uppercase. So if you see something that's uppercase, it's going to be a field, and if you see something that's lowercase, then it's a variable, it's some sort of scalar variable that scalar term that indexes into a sequence. There's at least one thing that is duplicated, which is this bit indexing function, bits function basically. There's one that's like symbolic and one that's like bits in Roman, in like typewriter letters. I'm gonna deduplicate those. Grandpa referencing, maybe a little the EC referencing potentially as well. And it's for 0.6 that we'll really try and get the test vectors complete for the for the M1 stuff, possibly some of the M2 stuff as well, definitely for the M1 stuff. What the test vectors should cover the full range. Like, I'm not saying they're going to be the final test vectors, because there'll still be tweaks to be made, but they should be complete. They should be comprehensive.
What do you mean by test vectors? They implement the test vectors in the JSON files, all this stuff will be ready together with 0.6. This is what you mean.
Or are you talking about the milestone 1?
Yeah, the
canonical test vectors. This is a sequence of blocks. You need to be able to import to come to this block hash.
Basically, yes. Now that I'll go on to this a little bit later because it's not the thing, but if you like, this is the training data, right? Not the actual final test data. That's separate, and that's not given to the team. That's internal to the Web3 Foundation. But the training data, so the information that you get for testing implementations against, that should be comprehensive by the time that the 06 series is complete. I mean, we're getting there, but you know, there's a bit more to come, and that's the aim of that. Ties roughly in with the lifetime of 06. Because after 06, there should be no more features coming. It should really just be tweaks based on usage. And in fact, even within 06, there's not that much here that's features, right? There's the MMB stuff, which is sort of a feature. But the JAM NP is already specified just outside of the grey paper. Grandpa's already specified. So in fact, 06 isn't really bringing anything new. It's just tying everything.
So do we get then the actual blocks to be inputted also at the end of the 0.6?
Yeah, I mean, yes.
Okay, that would be cool. Thank you.
And with 06, I mean, it might be 06, might be a little bit later,
yeah.
But around this time, 06, 07, is where we'll try to provide test harness requirements. Test harness requirements will be what your implementation needs to do in order to run our internal conformance tests, right? This is probably going to be an RPC interface where there'll be 2 or 3 or 4 different RPCs that are basically like, take this message, pretend this message came from a network, maybe one of them, import this block data, is almost certainly going to be one of them, and tell us what message you want to send to someone on the network, maybe. The networking, we're not sure yet. This may happen also just as a sandbox thing. So we just provide a fake network sandbox, and you just have to run under a Docker environment with this fake network configured. But for M1, there is no requirement for networking anyway, and so for M1, it will probably just be here is a stream of blocks. Import them and tell me what your state is. And we will specify that RPC. When we get to M2, as I say, there'll have to be some sort of networking thing. So whether it's an RPC and it's up to sort of the client to fake the networking for itself, or whether we provide a Docker environment with a fake network and the client can just pretend it's on a real network. Uncertain yet, but it'll be one or the other probably. And then it will basically be checked on not only what its state is, but what networking it sends out. And then when it comes to M3 and M4, it will be when it sends the networking out, right? This will be crucial.
So in the end, you know, say, so imagine essentially, you know, we're all done with this, and anybody could design a client, run it against the toast, right? Because that's how it's called, right? And then you can actually like verify the whole implementation. Yeah.
Yes and no. So you'll be able to verify against the training data,
yeah,
which we'll publish some of. But then, when it comes to actually doing the conformance testing,
yeah,
and for that matter, the performance testing, this will happen with procedurally generated data.
Ah, okay, yeah.
So you won't know what you're going to be testing
exactly.
ahead of time.
It's kind of like network fuzzy.
Yeah.
Kind of. Okay. Cool.
And as more implemented, so initially it'll be the Polkadot implementation that we'll be doing the conformance tests against, and then as we gain confidence, like basically as other implementations pass the conformance tests, they'll also be part of the fuzzing thing.
Yeah.
Right, and
that's cool.
As we find compatibility issues, so basically as the conformance testing finds issues, we'll isolate these particular circumstances and they'll become part of the training data.
Oh, that's cool. And is this then, say, deterministically generated, this procedural stuff? Well, like for example what Tiger Beetle did, I don't know if you're aware of this. They got this kind of random number and everything, you know, everything is generated out of this random number, so you can actually replay, you know, to find.
Oh, I see what you mean.
Yeah.
Yeah. Quite possibly.
Yeah.
Yeah. I mean, we should be able to assuming that the cradle itself is deterministic, we can certainly reproduce the input data that gave the problematic situation to arise.
That would be cool.
I have one question about the performance, milestone 3 and 4, since you touched on that. I believe I recall some mention about having some sort of relative performance benchmark. Is there any
indication of how relative?
Yeah. So there will be a best performing client, likely, and a worst performing client.
That's a cool idea.
So what does Polkadot performance actually mean in objective terms, or what does Kusama performance mean?
So Polkadot performance is probably going to be within some particular percentage of the best performing client. So let's say, finger in the air, 80%. So on average, work package execution and block import must happen within 80% of the time, within 100 and whatever, 25% of the time of the fastest implementation. Then there's the question of like what we require for M4 as opposed to what we require for how is this going to work? So in essence what we want is to say there must be 3, that's it. So all 3 implementations before we launch the network, there must always be 3 implementations that are that anyone can run. So before we launch the network, we want these 3 implementations to be no slower than 80% of the speed of the fastest implementation. That's the condition for launching the network. Once the network is launched, once we have these 3, then what we want to do is do it not on the basis of the fastest one, because the fastest one might get faster and then there wouldn't be 3 sufficiently performant implementations, right? And we'd be like, we've got to stop the network until this guy gets fast enough to then be 3, that's no good. So then we take it on the 3rd fastest implementation, and we say you must be within, let's say, 5% of the 3rd fastest implementation, which means you might get knocked out of the top set. Like if you start off as being the 3rd fastest implementation, and then some other implementation comes along, passes M5, and they turn out to be sufficiently faster than you and the 2nd fastest implementation, that you are no longer within 5% of them, then you would no longer be like considered a sufficiently good implementation for validators to run. Right, so there's like going to be a continuous competition to like be within 5% of the 3rd fastest implementation.
But some thought has gone into this, no doubt, that will be shared in due time.
Yeah. For now, it's like focus on it more. Right, so then 07. So there are probably some. I can already think of some things that we're going to want to change when we, probably by the time we get to putting things on the toaster. Not least the network protocol. I know there's at least a couple of things that we want in the network protocol that aren't in there at the moment. So that's probably where the bulk of the grey paper changes for 07 will be, I guess. We'll probably want to optimize the erasure coding. We'll probably want slightly different erasure coding parameters for work bundle erasure coding compared to segment erasure coding. At the moment, they both run on this, 682 byte sort of chunks, which is not especially, because the thing is, if you're doing it using a regular sort of binary erasure code, then it has to be like 2 to the 9, like 512 that you're going to be working on, not like, you can't work directly on this 342, 341. size, right? And this means that you're wasting a third of your points. You're basically doing an erasure code for a 512 point data where you actually don't care about the last third of them, and that's not so great. So we'll, it's kind of fine for doing the segment stuff because, you know, just the way it works out, it's probably the optimal way of doing it, just because of the amount of, it's really hard to parallelize on the CPU, at least with the current algorithms, and the number of, it's still substantially faster to do a 2 to the 9 than, like, it's still substantially faster to do like 8 2 to the 9s than like 4 2 to the 10s on a CPU, because you can usually do about 16 at a time anyway on a modern CPU, and unless you're thinking everything is going to be coming from the same index or set of indices, then you're not going to be able to parallelize. If we can get it so that if we find an implementation that allows for segments to be coming from, or chunks to be coming from different sets of validator indices, different sets of indices essentially, then this changes, and we probably do want to alter the segment EC, but for now I think it's probably optimal. The work bundle EC definitely is, it shouldn't be that, because the work bundle is going to be coming from the same validator indices, and there's going to be like megabytes of it, so it's inherently very parallelizable, and so we want to work at the highest size possible, and that's probably what we probably go up to 2 to the 12, 2 to the 13, whatever. We've got some benchmarking on it. It's definitely not 2 to the 9. We know that much, and even if it is 2 to the 9, it's definitely not only using 2/3 of 2 to the 9. Yeah, data logistics optimizations probably, again, these go hand in hand with the JAM optimizations. Just making sure that data gets between nodes quickly and easily. And then there may be PVM tweaks that we need for, I've put here inner continuations, which is basically the ability to suspend and resume PVM instances between blocks. And this is one of the key features of JAM. Basically, the ability to run a virtual machine and make it look within the virtual machine as though it never stopped running, even though it's running between many different blocks. We may need to tweak. We may need some tweaks to that. We won't know until we actually start coding with this stuff. 0.8, as I say, is like continues along this theme, but rather than post-host to post-service prototyping. Maybe, so one of the things that I've touched upon a little bit in the JAM chat room, but is very important point, is the difference between accumulation and integration. So accumulation takes like the results of a work item and does some code, right? Executes some code on these results with access to some synchronized database, the on-chain database. But it doesn't necessarily integrate it into some final world model that this service maintains. It could, for example, queue those changes or discard the changes entirely, or queue them and then eventually discard them, but unknown at the time which will happen. Now, what integration is what I'm calling this this higher level concept of without the possibility of ever reverting, committing whatever these changes mean for this service into its state. And it's integration that we care about when we're doing cross-service composition, right? If you're if you're, I don't know, sending a token exchanging a token between two services, a very simple, crappy example, you want to know that the token has actually gone from one service to the other one irrevocably before you do the same on the other side, right? They have to both have had this high level state integration. It's not enough just to say, well, I know that the other one has run its accumulation code on this because hey, maybe the token doesn't exist anymore, maybe it was somewhere else in the meantime, or whatever else. So integration is this higher level effect of accumulation that isn't necessarily, I mean, if you've got like a totally conditionless, totally infallible accumulation code, then they're amount to the same thing. But if your accumulation code has conditions in it, or different things may happen depending on what's just happened before, or could fail in some way, then they're different things, and you need to ensure that you need some means of ensuring that integration has happened when you're doing cross-service collaboration. Maybe this is worth it actually having as a facility inside of Jam. Maybe. Don't know yet, haven't developed any services yet, haven't tried to make services actually interact with each other yet. But when we do this, we might find that there are certain patterns that are very useful and inefficient to implement with existing primitives, and we actually want to have some additional primitive for specifically this.
Would this allow distributed atomic transactions?
Basically. So, it would allow you to say, right, I know that this other service wants me to do this thing, but I don't want to do this thing until I know it's done that other thing that I want it to do in return. Yeah. And it's essentially going to be this synchronization.
You could actually do like a state change over multiple services.
I mean, the way that it would be done at the moment is Service A and Service B may have what I've called an entangled work item, which is a work item that, there's two work items, one for Service A, one for Service B. They're codependent. So their effect on their service's state is conditional on the other one having an according effect on its service's state. Yeah? And it's like you don't want to enact one of them without being sort of guaranteed that the other one will be enacted as you expect. And it's not enough just to assume that they're both going to hit accumulate, unless your service is trivial. If your service code is trivial in both cases, then you can probably just assume if accumulate happens, then it's probably fine. But unless it's trivial, then you need some sort of thing of, hey, I got this work item, and as long as I hear that you got your work item and are cool with it, I am going to do my thing. And it's kind of like, I'll do this. It's like saying, I'm ready. Are you ready? And as long as you get the I'm ready from the other side, then and you've sent the I'm ready to the other side, then you can go ahead. Because you know that the other side will go ahead. But you have to wait for this I'm ready, yes, I'm ready too thing. And it's like, maybe we want a facility for doing this. Maybe we don't. A way that you could also do it is just storage. So in your service storage, you have a special place that's like, I am ready I've received this work item, I know it's entangled with your work item on that side, I'm ready to enact on this. Once you're ready, I'm going to read your state, and if I see that you're ready, I'm going to enact it. But probably you wouldn't want to have to read it every time, so you probably want like some sort of transfer message. And I mean, it's doable, totally, it's possible, but maybe we want a facility for optimizing it, especially if we expect lots of cross-service composition. We may want tweaks to the PVM. That's, I think, less likely, but it's possible. We may want tweaks to the DA. We may want tweaks to the work package dependency system, so the ability to have X dependencies, the ability to have these segment root work package hash lookup system that was just introduced with accumulation. And then in general, there are a bunch of things that, as I say, represent the success criteria of Jam, like core chains, core play, inter-service composition. And as we start implementing this stuff, we'll be better able to understand whether the Jam protocol as it stands can actually serve these needs sufficiently well. So that's where I see us getting into 0.8. And 0.8, after 0.8 is done, it's like, right, this is Jam 1.0, right? This is actually our kind of 1.0 stick in the sand. We're not adding anything new at all at this point. We're not tweaking it. It's just what it is. 0.9 is it goes off to audit, and the only things we change are what comes back from audit. And then what is 1.0? So service development, which probably is kind of helpful to know what's coming. As I said, I'm kind of in a pretty good position to be starting to fiddle around with services now. Once I've got 0.5 out of the way. It'd be really handy to find someone to do some of this grunt work on the grey paper. It kind of takes quite a lot of my time. But anyway, until I find someone to do the grunt work, I guess it's me. So it's not going to be my 100% focus, but I should be able to dedicate quite a bit of time to it anyway. And first thing will be this basic JAM SDK. So this is something we can publish. It'll have all the basic data types in, and just basically a Rust build system, so you can code a JAM service in Rust and build it into a PVM executor. As I say, yeah, I'm hoping to get that. We already have it internally. It's just it's kind of tied into the rest of the code base, so we need to like isolate it a bit, tidy it up. By the end of the year, it would be nice to have the final core boot service, which is this bootstrapping service that we can put in a Genesis block. And probably will also, I've not mentioned the authorizer the authorizer code for this. I mean, there's a null authorizer which is just returns true. It's not very, it's like very, very easy bit of code to write. But maybe we also need this as well. I don't think it's that important at this stage though. We have, ideally in the first quarter of next year, what I've called Core VM, which is so Core Boot basically has instructions, a vec of instructions as a work item, which get passed into the refine stage. Instructions might be creation of a new service, designate a valid group, assign core time, blessing a new service, so basically taking another service and giving it its privilege. Introducing always accumulate services, new with 0.4. Transferring balances or soliciting and forgetting privileges. Right. So all of the stuff services can do, basically. So then the thing after that to be coded up is, as I say, Core VM. This tests the inner PVM functionality. And this, I think, is really, once we get this working, it's like, there's a big weight off the shoulders, because it's like, if it can do this, it can probably do everything else. And this will probably be where we base the performance tests. So for M3 and M4, would be more or less how fast can you run Core VM, and how many of them can you run. So it's, the concept is you just give it a regular no STD compiled binary, and it can just run it like a regular computer can run it, and there'll be some I/O, so you can like basically have like a database layer. That'll be your main I/O. You can write stuff into the state storage, sorry, the service storage, and read stuff out from it. Maybe not read stuff out from it, but definitely write stuff into it. There is nothing special about the binary, right? That's the clever thing. The binary is just like a regular binary. If you want to put an infinite loop in there, you can put an infinite loop in there, and it will just still work as you would expect if you run it on a regular machine. The VM executes as part of refine. RAM is stored in the segment DA, like each data lake, and paged in and out as needed. And the VM is clever, it's suspended and resumed as it needed, so if it hits memory that isn't in the work item, that isn't sort of, that can't be fetched in as a page because you've already fetched in too many pages or whatever, it just suspends the VM and it continues it in the next work package.
I find this very interesting what you just said. So you can actually make an infinite loop, and it will just run, and then it gets its slides. It will be just suspended, and it will continue. So actually, the punishment is now if you write bad code, but you're broke.
Yeah.
That's
Exactly.
cool. Yeah.
Exactly.
Yeah.
Like you don't need to be concerned about
No.
gas. I mean, you can be concerned about gas, but it's just going to cost you more.
Yeah, exactly. Yeah.
And if you're willing to stuff up the cash, then just write whatever code you want.
So it's different in terms of like comparing to Ethereum. Ethereum doesn't let you, if it's too much gas to use, you just can't.
Well, you can't execute it.
You can, in this case you can, but you just spend a little bit
Just trying to
on
stop
each
it.
iteration.
Yeah. And I mean, realistically, if you're writing just regular, if you take Doom and compile it, the point is you should be able to build Doom and run it in Core VM, right? In Jam's Core VM. It won't run very. Oh, I don't know actually. Maybe it will run quite fast. But the thing that will be the limiting factor isn't the compute power; it's the memory bandwidth. Because every 4K page you hit, then it has to come in. You can only have in every 6-second work package 2,000 4K pages. So if Doom fits into 8 megabytes, which it might actually do, then it should run at almost native speed.
That's cool. That's cool.
Yeah. So and the idea is that this will
probably some old games will actually run.
Yeah, I mean,
Atari games.
What you can definitely do is take I don't know, like an Amiga emulator or a Spectrum emulator and just run it in real time on chain, which is pretty bad.
We should create a contest for that, some sort of nonsensical contest. That will be fun.
Nonsense services.
But back to your original question, I think also as a programming model, it's like kind of like we are stuck in this way of thinking where things are like blockchain programs are like this block-based and transaction-based things. Like even today, if you want to write like a substrate chain that kind of just fills the block with an infinite loop, you still have to think of it like you have to write it. It's not like one entry point. It's like you have to think about like you run and then when you resume next time, what do you do? Like it's a very different way.
Like multiple migration is just so complicated.
Yeah, exactly. Like that's how it looks in the current model. But in the new model, it can just be a main function.
Yeah, it will be just big while.
Yeah, exactly.
I mean, it's kind of mad to even move into this paradigm. We're so used to the other one.
Bends the mind to it.
But that my hope is that we can sort of start taking regular, graduate or undergraduate level programming books and actually just write these algorithms, write these pieces of code. I don't know, maybe you have to translate it to Rust or whatever. Probably not though, because like C++ can be, C can be compiled into PVM pretty easily. And just execute it on chain and say, well look, it's just a regular coding.
Let's try to wrap up in
5 minutes? Alright, sure. I'm on to I think it's almost the last slide. It's got 2 more left. Yeah, so then after that, midway through next year, probably going to be more like Q3, I guess. We have core chains or whatever it is that Sean wants to rename it to, which is basically just the replacement for the relay chain functionality. So it does message passing, finality, fault tracking, and runtime execution verification.
I remember
someone. I'm kind of hoping to put it on. I mean, we'll probably the Poker Jam team will probably start on this and do some prototype code just to sort of show roughly how it should go, and then I'm hoping to basically get the substrate, the current Cumulus team, at least 1 or 2 of them. Maybe we can just form a 2 or 3 person team and do it. But I mean, the logic's already written, right? It just needs porting into a service. So I'm kind of hoping it's not going to be that much effort for them. And then finally, Core Play, which is Core VM plus the hard thing, which is the inter-actor composition. And this is still a little bit of a unsolved problem. I think in general it's an unsolved problem. It's not that it's unsolved for us. It's just like if you have arbitrary numbers of actors with arbitrary constraint satisfaction requirements, like basically that where they can't run unless that actor gets to this point and this memory has been fetched in, and there's this amount of gas free to be used. And then you have to basically take all of these constraints and like create the optimal partitioning of actors into separate synchronously composable pockets with amounts of gas for each one and execution ordering for each one, kind of scheduling for each one. I think it's pretty hard, but it's what operating systems schedulers do all the time. So I think it's also not. It might be theoretically unsolvable, but I think there are algorithms that get you quite far, just heuristics and so forth. So yeah, I think it's probably doable. Then the question is whether it's doable in like a decentralized fashion. Probably not in any really secure way. But then the question is, well, how secure does it need to be? It's probably fine even if it stalls for like a block or two, as long as there's like a way of like doing leader passing and making sure that the same one leader can't just stall the network for a sufficiently long period of time.
I have a question. Let's say, would it be possible to have like kind of a service which you just want to run, like for example today, and then when it's necessary, next week only one state transition, and 3 months later another state transition, and for the rest, actually I don't care. I just want to inherit, let's say, the fundamental, security of the network.
Yeah, there's nothing. I mean, as long as you're willing to keep a deposit down for the storage costs.
Okay, definitely. But let's say, can I just only pay for when I use it?
Yep.
And then the scheduler will just give me some time just to execute.
That's not specifically within core play.
Okay.
Core play is the service.
Okay.
That would be an actor within core play. And then the question is, well, are you willing to, like with core play, the actor's memory would be stored in the distributed data lake, which keeps it around for 28 days. If you don't hit your actor, or if you don't hit one particular page of memory of the actor for more than that, then it wouldn't be there when you want to run the actor again. Okay. So there would need to be an additional service that basically checked to see that if your actor is getting old, and if it's getting old, to store that data in some other longer term data storage. So
kind of keep alive thing.
And then you'd have to pay for that service to do it as well, right? And this is why I say that actually having probably a long-term data storage service sitting directly on JAM is probably a sensible one. Like not in JAM, but like as a first-class thing rather than as a parachain.
So it's almost like a pinning service, IPFS pinning service. Just like keeps it alive.
And that's it.